in a lot of what we've been studying so far, entropy, cross entropy, and KL divergence, we are dealing in a field called information theory. And so, as you're noticing here, hopefully, we are looking at information and we're trying to generate some sort of metrics from it. Now, the historical underpinnings of information theory deal back to a man by the name of Claude Shannon, who wanted to think about how many bits of information needed to be communicated in order to say send information across long distances. And so what's the minimum number of bits that would be required to do that? But the application that we're using it for here is a little bit different, yet it's taking those same principles. So if you're interested, go read about Claude Shannon. Okay, so last principle here that we'll investigate in the realm of information theory is called mutual information. And as you might guess, it gives us information about things that occur mutually. And let's make that a little bit more clear. So in this case, suppose we collect some data and we're interested in seeing how the pairs of variables are related to one another. So I might give you a height and weight, and maybe we want to figure out how related people's heights and weights are for those same people, right? How much is, if we know somebody is 60 inches tall, based on the demographic, can we describe how much they weigh? Many other pairs of variables, they don't have to be continuous. In fact, we'll see an example of where the variables themselves are discrete. So in something like a regression analysis, linear regression, nonlinear regression, you might use something like R, which is the correlation coefficient, or R squared, coefficient variation. But another way to do this is, especially nicely for the discrete case where we don't have numerical values, or at least not continuous ones, we can create this metric called mutual information. And you're going to notice that it looks somewhat similar to entropy, cross entropy, KL divergence. Looks a lot more like KL divergence, but we're not going to unpack really the derivation here so much. But I of x comma y, the information between x and y, is the sum across all x's and y's. So basically, you're going to, if you have, let's say x, the cardinality, or the size of set x, the number of instances of that random variable is maybe 3. And in y, you have, say, 4 states. So 3 times 4, that will tell you that there will be 12 terms. Each one of these 3 has to pair with each one of these 4. And so you'll have 12 terms as a result of that. Now, one thing that I want you to notice is that if the probabilities were exactly the same. So here we have a joint probability, right? The probability of, we might write it as x and y. And then we have the marginal probabilities, the probability of just one event without regard for the other. Now, one thing that we know about Bayes' theorem is that whenever you take a joint probability, and if those two events are independent, okay? So, independent events, if two events that are independent, meaning there's no relationship between how their probabilities affect one another. If you had 2 independent variables, then it would follow that the joint probability would be the product of the individual probabilities. So what I'm trying to do here is establish a framework for situations where 2 variables are totally independent, 2 random variables. Well, in that case, if the probability of x comma y, or the joint probability, which is this numerator up here, okay, this is a scaling coefficient. This gives us a weight for each term based on the joint probability, and you divide that by the product of the marginal probabilities, which is this. Well, if they are equal, then this ratio would be 1 inside of that parenthesis. And the log of 1 is equal to 0. And if if this were true for both random variables and you sum these together, you would get an information value between x and y to be 0, meaning they are very, very poor. They're not related at all, which makes sense based upon that. So you can use that sort of as a framework for how this thing is designed. If they are not independent variables and there's some relationship with them, then we would write for two dependent variables, it would be that the probability of x comma y is equal to one of two things: the probability of x times the probability of y given x, or the probability of y times the probability of x given y. And so notice that the second probability, it may not match that of the probability under the fraction here, and so they're not necessarily going to cancel out and give us 1 and then provide a log of 0. They'll be somewhere bigger, a value bigger than 0. Okay, so any term, by the way, if you get a log of 0, we're going to set the result equal to 0 instead of it being undefined. Okay, just keep that in mind, that if you do see a log of 0, in this case, we're just going to define it to be 0. Okay, so let's suppose we have this data, and we're going to take a look at two cases just to see that in one case, the mutual information is going to be higher than the other. And let's just say we collect some data. Now, we could have lots of variables that we collect on people. We just want to look at pairs at a time. So let's say we're comparing, we can survey 4 people. We ask them their vehicle type that they drive, and we ask whether they explore the outdoors. So they do outdoor things like hiking, fishing, etc. And so 0 will be a car, 1 will be a truck. In this case, notice that we have 2 people that drive a car, and one of them does outdoor things and the other one doesn't, right? So if I said, okay, I know a person that drives a car, how likely is it that they drive a truck? Well, you'd say, that they do outdoor things. You would say, well, I don't really know, because it could go either way. And you'd be right. And then a truck or SUV, in this case, notice, again, it has no bearing on whether the person enjoys the outdoors or not. So we would expect that there isn't a high level of correlation. So not much. I'll just say not much. Because there's definitely, maybe we do get a measurement that's non-zero, but there's not much mutual information here. Okay, so let's set this up. So to calculate the information between x and y, I'm going to have to sum across all x. So x, if we think about this as that x and y, then we have to add across the vehicle type. So x will either be a 0 or a 1. And then here we have to add across all y, which is an element of yes, no. Okay, sloppy notation, but good enough. And then the p of probability of both of those things times the log of the probability of both of those things divided by the joints. Okay, so I need to come up with, if you notice here, we're going to have 4 terms in this. When x is 0, when y is yes, and when y is no. When x is 1, and then when y is yes, and when y is no. So I'm going to write it this way. I'll say 0, comma yes, and then we're going to have plus 0, comma no, and then 1 plus 1, comma yes, and 1, comma no. In any order, but these are just the 4 terms that will be applied. So in the case where x is 0 and y is yes, we need to compute the probability of that, right? So the probability of x and y in this case, of 0 and yes, and write it this way, the probability of 0, comma yes, again, I'm being a little sloppy here, I should say x equals 0 and y equals yes, but we can calculate that, right? We can say, well, what percentage of the outcomes, there are 4 of them, what percentage are 0 for vehicle type and yes? Well, there's only 1, right? 0, yes, there's 1 out of 4. And now we need to know the probability of somebody driving a car, which is 1/2 or 2 out of 4. And then we'll need the probability of yes, without looking at vehicle type, which is 2 out of 4. Okay, now notice if you take 2/4 times 2/4, you actually get 1/4, which further reinforces the fact that the mutual information here is going to be very low. Okay, now let's do the same thing. Probability of 0 and no. Okay, well, 0 and no occurs only in 1 out of the 4 instances. The probability of 0 we already know is 2 out of 4. Probability of no, that's 2 out of 4. Again, and this 2 probabilities here, these are marginal, meaning you're not looking at the other variable. Probability of a 1 and yes. Okay, well, that only occurs in 1 instance. That's 1 out of 4. Probability of a 1 is 2 out of 4. And the probability of a yes, we already know, is 2 out of 4. And then when you do one more here, we'll have the probability of 1 and no. Again, occurs only in 1 instance, 1/4 of the time. Probability of a 1, we already noticed, was 2/4. Probability of a no would be 2 out of 4. So notice what's going to happen here. The information, so it'll be the probability, which is the joint probability, which is 1/4, times the log. Okay, now we'll just use standard log here. It doesn't really make that much of a difference as long as we're sticking with the same log for all the terms. We'll have 1/4, the joint probability, divided by 1/2 times 1/2. Well, notice that this is going to equal 1, and the log is going to equal 0. So again, we'll get 1/4 times the log of 1/4 over 1/2 times 1/2. Again, these are actually all the same. 1/4 log 1/4 over 1/2 times 1/2 plus 1/4 log of 1/4 over 1/2 times 1/2. So in all of these cases, these arguments are equal to 1. And that, as we saw, will lead to all of these having 0 outputs, and the information, in this case, between x and y is 0. So really, we indicate that there's no correlation. They don't correlate at all. Knowing one tells you really nothing about the other, because just because you drive a car, it's just as likely that you do outdoor stuff as you don't do outdoor stuff compared to when you drive a truck or SUV. So there you go as an example with independent events. But let's say we collected this data instead, which is highly correlated, right? If you drive a car, not that you can't do outdoor stuff, but just to make this something more interesting, the people with cars don't do outdoor stuff, and the people with SUVs or trucks do outdoor stuff. And so we would expect that these are highly correlated, that knowing the vehicle type necessarily tells us a lot about whether or not they like doing outdoor activities. So once again, we'll set this up in a similar way. We'll have 4 terms, 0 yes, 0 no, plus 1 yes, plus 1 no. Okay, so the joint probabilities, probability of 0 and a yes, will be 0, right? It'll just be 0 out of 4, which is 0. The probability that you drive a car is 2 out of 4, or 1/2. Probability that somebody does go outdoors is, again, 1/2. So notice that in this case, 0, 1/2 times 1/2 does not give us 0. So that tells us that these are not independent events. Probability of 0 and a no is going to be 2/4, which is 1/2. Probability of a 0 is 1/2. The probability of a no is 1/2. So 1/2 times 1/2 doesn't give us 1/2. Again, we see that emergence of correlation here. Probability of 1 and yes is 2 out of 4. And the probability of a 1 is 2 out of 4, or 1/2. Probability of a yes is 1/2. And we could kind of do the same thing here. This is equal to 0. Probability of a 1 is 1/2. Probability of a no is 1/2. Now, by the way, these two terms on the two ends are going to give us log of 0, because we'll have the joint probability, which is 0, times the log of the joint over the product of the marginals. Now, this is undefined technically, right? Because log of 0, you do that in your calculator, there is no exponent. There is no exponent such that raised on the base that 10 to a power will give us exactly 0, and that's the definition of a log. So this is technically undefined, but it's really about a limit. So as x gets really large, or as x gets really small, excuse me, then the x log x over 1/4 will get really, really close to 0. So we're just going to basically say this is 0, and then we will do the same thing here. We'll take plus 1/2 times log of 1/2 over 1/2 times 1/2. This will be the same term over here, just based on the nature of how we selected these probabilities. And for this last term, we'll have 0 times log of 0 over 1/2 times 1/2. Again, this will be 0. So what do we get for mutual information here? Well, we just need to add up these two probabilities. We'll basically have two of these. They're the same. So we have log of 1/2 over 1/4. And we get a metric of 0.30. It is the approximate value that we get. So there is correlation between vehicle type and outdoors. Okay, now what does that metric mean? Well, it's not so much about this metric itself. It's all about the metrics relative to one another. So if we had more columns of data and we compared other pairs of data, like maybe vehicle type and whether or not a person wears, what kind of footwear a person wears, and we compared all those informations, then it would be all about the relative mutual informations compared. So clearly, if we compared two variables and they had a mutual information of 0 compared to a mutual information of 0.3, that is much, much, much higher. And in fact, we see that they're perfectly correlated in this situation. So the metric that we come up with is kind of a function of how many states you have for each of the variables, right? Because there'll be a separate term for each variable and the probabilities themselves. But at least if they are completely independent, we do expect 0 mutual information. And so as expected, we see that case 2 contains variables that are more related than in case 1.